Since we're doing matrices and my clicker's not working because it's a different computer and I tried to hook it up on Bluetooth, so oh well, it is what it is. So what I've done for you also, I keep learning. I taught a class, my first ACT class for this section last week, and no one took notes in there either, and I went, oh, it must be a new teen thing. No one's taking notes. Like everything I'm saying is important, write it down. But if we had a paper, we'd write it down. So some of the practice problems that I will have on the board that we typically kind of talk about, I've printed those off for you. So then you can actually write it on there. So you kind of have some real live notes. So as you see these, go, hey, that's this sheet. You also have matrix notes. This is part of your homework, so we will work on these and fill out stuff as we go along, but this is part of your homework too. So when I say the matrix note packet, that's this packet for it. Okay, so matrices, lots of new vocabulary. Again, if we don't know what we're talking about, then it just feels like we've been thrown into France and we don't speak French, right? So matrices, I explained a little, I was chatting a little bit about beforehand. Why are we going from math and variables and all these equations to now the next chapter is matrices, and it's just a bunch of numbers in these brackets? Like, it feels like something just got thrown in, like, oh, here's something from Mars and we're going to talk about this now to give ourselves a break. It is not that, okay? When we look at matrices, they are the coefficients of systems of equations. We've just gotten rid of the variables. So now we're looking at just combining like coefficients. And so we will talk about that more next week, because in your book they don't address it until later. You guys know that I hate starting on a journey without telling you where we're going, because it's like, I want to know, like, are we going to California? Like, how far are we along the way? What does it get us to? That way your brain has a little bit bigger picture of it. So we're going to be going towards solving some systems. It's a new way of solving systems of linear equations, just like we did for the last 2 weeks. Instead of doing the combine and find one, combine and find, combine and find, it's just a new way. It's a different way. And you can walk away from this chapter and go, I like the old way. I'm going to do it that way. Okay. Or you can use it this way. I do want you to have seen them, because if you've never seen them, they'll freak you out. They are on the ACT. So in one form of another, usually it's the simplest form. This last one actually had a multiplication form though. So again, we're just going to kind of expose. We're not going to deep dive into it. This isn't a make or break chapter. Okay, so have fun with it. We're going to try to have some fun with it. And then next chapter, we'll hit quadratics. Big deal, big chapter, lots of weeks on it, lots of stuff. We'll have lots of fun with that. Okay, so vocabulary that we need to know. A matrix, if they're plural, it's matrices. Again, dimensions of a matrix. This is the most important vocabulary word on the entire thing. Dimensions is how you read a matrix. So a matrix is going to look like this, and we'll have some more practice earlier, and it's going to have numbers in it. Okay? Different orders of numbers in it. A matrix, when we have dimensions, it is read as an L. Okay? So we read down, and then we read across, and we're just counting numbers of rows and columns. So this is 1, 2, 3, 1, 2, 3. So this would be a 3 by 3. Okay, we read down, and then we read across. Okay, very simple, but that's what it means when we have dimensions. When we're looking at the matrix and we talk about the entries, that means each individual spot is called an entry. Okay, that's all it is. It's just the different numbers on the inside. Scalar is an interesting term. Scalar, you might see on the ACT, the SAT, entrance exam or something. A scalar is when you have a number in front of your matrix. And while this matrix is not a parentheses, when a number is in front of it, it is treated like multiplication. Okay? And so then we can kind of act. So it's like it's not a parentheses, but it kind of is a parentheses. It's a big parentheses of a bunch of things. Okay? So that number is called a scalar. Okay? If the matrix has a solution, it is defined. That's all it means. If it has a solution, it's defined. That's like if a system of two equations, like we learned last week, we have two lines that cross, it's defined because it had a solution. Mm-hmm. So when would a system not be defined?
When it doesn't have a solution.
Yeah, and what kind of system of equations was that when they weren't defined?
Like what type they were?
Yeah, how did the lines have to look?
Well, parallel.
Parallel. On each other had infinite solutions.
Oh, that's right.
Okay.
Parallel.
So parallel lines would be not defined. Crossing lines would be defined. Same thing. So defined means it just has a solution. Okay. Product. Product is multiplication. We've always learned product is always multiplication, right? So we've learned before that if I say 4 times 6 is the same as 6 times 4, correct? Because in the very first week we learned that this is the commutative property, right? Commute from one place to the next. Okay. Matrix multiplication is not commutative. Okay, so that's a rule that we need to know. It matters what order. It is not commutative, but we're still going to multiply. It still means multiplication. Okay. Determinant is this funny answer. Okay, it is a single number, okay, that defines all of these answers. So you might come up with 2 or -5.
Would it be 3?
Whatever. What?
3?
No. So we'll learn how to do the determinant next week. It is a single number that tells you an answer about this.
Oh.
It's used further on in some mathematics stuff, but it's a specific number that all of these numbers together are defined in one number.
Okay.
So that's what it's called when it's a determinant. We'll learn that next week. Coefficient matrix is basically just a matrix. When we have x plus y and 2x plus 3y, could I say those are both 1?
Yep.
If I erase all of my variables, of that system of equations, I have made a matrix. That's how we get them. That's where this comes from. All we've done is erase the variables. Okay? So you can hear it said as the coefficient matrix. That's if it has had a system of equations and we've just put the numbers in front of it. Sometimes you'll just see it straight as a regular matrix. But, so when you see this grouping of weird numbers, and you're like, someone just lined up a bunch of numbers. It's actually, these are all x values, these are all y values, these are all z values. So this would be x plus z, right? X plus 2y plus 2z. X plus 2y plus 3z.
Okay.
All right? That's all it is. So these are not scary. It's not anything.
Do you ever have to graph a matrix?
No.
Okay.
No. Okay. So Kramer's rule is a special equation that we can use to a shortcut for finding systems of equations. The identity matrix is a very special one. It has 1s along the diagonal, and we'll explore that a little bit more. But we know that when we're dealing with multiplication, identity is the value of 1, right? So it always gets us ourselves with it. And then the inverse, what do we know about the inverse? The inverse always gets us back to the identity, right? So 4 times 1/4 gets us back to 1. So the original times your inverse always gets you back to the identity. So the same thing works with matrices. When we have a matrix, if we had an inverse and we multiplied, it would get us back to the identity. So the same rules that we learned in our regular mathematics, our basic algebra, are still applying here as we deal with matrices, okay? So, types of matrices. There are row, column, square, and zeros. So there's 4 different types of matrices. Rows mean that your matrix only deals with a row. So it's just going across in one row. It's horizontal. It doesn't matter how many entries are in it. It's always just a row, a single row. So a column is just a single column. It doesn't matter how many entries are in it. It's always down in a column. Okay. Square means that there are equal numbers of rows and columns so that we have a square. So we have a 2 by 2, 3 by 3, 4 by 4. Could go on as big as you want. Okay. And a zero matrix just means there's zeros all over the place. Pretty easy. Right? Okay. So labeling matrices, they're always labeled in L format. We read the rows, the number of rows, and then the number of columns. Okay. So in this one, we're going to label these. So we would go down. How many rows do we have? 1. And we're going to do by, which is an X. It's not multiplication. This is read 1 by.
Okay.
And then how many columns do we have?
2.
1 by 2. What would this one be? Oh.
Let's say 1 by 3.
1 by 2. What would this one be?
1 by 0 by 3?
1
3.
by 3. So this one happened to have the same numbers. We're not dealing with the numbers. We're actually looking at the places in it. So we have 1 row. When we go down, and we have 1, 2, 3.
Okay.
3 columns. Okay? So this one we have
1.
1 row, and we have
4.
1, 2, 3, 4 columns. 1 by 4. Okay? So again, we're going to read these. We read them down and then across. So this we go 1, 2,
By 1.
when we go down, by 1. This one is a
3 by 1?
perfect
4 by 1.
and a 4 by 1. Okay?
2 by
We
2.
talked about this one. We've got 2 by 2,
3 by
3.
3, 1, 2, 3, 3 by 3,
4 by 4.
4 by 4. What is this one?
2 by 2. 4 by 3.
3 by 3.
3.
Excellent. Okay. Pretty straightforward with that. Okay, so now you should have a practice sheet that starts with 3, -4, 7. Yes, so we're going to label these. So let's do the top 4 and then we'll do those. So take a minute and label 1 through 4 on your sheet. All right. So the first one we got
3
3
by
by
1.
1.
perfect.
2 by 2.
Yep.
1 by 4.
Yep.
1 by 2.
Great. Okay. Now do 5 through 8. All right. What do we get?
3 by
3 by 3. 1 by 2.
Oh,
2 by 1.
2 by 1. Down first, then across. 2 by 1.
3 by 4.
Yep.
And 2 by 2.
And 2 by 2. Perfect. Okay, so you should match that. Okay, so row operations. Here's the thing. So some math rules can apply, and we can interchange our rows just like we could switch orders of numbers. The reason this is working, so just think about, my numbers are actually the coefficients of an equation. So could I write x plus 2y equals 3 and 3x plus y equals 4? I could write it like this, or I could write it 3x plus y equals 4 and x plus 2y equals 3, right? I could just switch them.
It's the same thing.
It's the same thing. So the same thing applies when we deal with matrices. So we can switch them. we can switch the different orders. So interchanging rows, for this one, like they just swapped. If we switch row 1 and 3, we would just take all the numbers in the exact same spot and we're just switching them in it, okay? Now, multiplying a row by a non-zero constant. This is our scalar, okay? So we talked a little bit, I was explaining we had that scalar value out front. So let's just do a nice, what is that kind?
2 by 3.
2 by 3. It's a 2 by 3, right? Down 2, across 3. Okay, if I put 4 in front of this, let's see what would this look like if this was really x plus y plus 2z, and I decided to multiply my entire equation by 2, I would have 2x plus 2y plus 4z, correct?
Well, why 2 but not 4?
You have to split it up. So if it's
Well, it's like the scalar is 4, so why did you?
Yeah, I did an example.
oh,
This
Oh,
is
okay.
mine. I
Okay.
was on a small little tangent.
No,
So
go ahead.
if I had it as a variable and I multiplied it by 2, I would just multiply the same thing to all of them, right? That is all that a scalar does. When we have a scalar multiplication on the outside, he gets multiplied times everything on the inside for both 3, 5, however many rows that we have. Every equation gets him. So this guy would change to 4, 4, 8, 8, 0, 16. Okay, so all we did was multiply it on the inside. And so that's called scalar multiplication. When we have a number on the outside, it will not have a sign, it will just be attached right on
Kind of
the
like
outside.
parentheses. It's just
Yeah, it's like parentheses, but they're not parentheses.
Yeah, yeah.
That's kind of way how it talks. It's like, but we have to kind of treat it.
Yeah.
Treat it like that, okay?
Similar system.
Yes. So there's also some things that they might say, like add a multiple of one row to another. So it would give an instruction of do 3 times row 1 and then add it to row 2. So in this case, we're just following the instructions. So 3 times row 1 becomes 6, -6, -3, and 9. And we're going to add that to row 2, and then that's now our new row. Okay? So sometimes it will give you some interesting instructions for that. Okay? So you can see that these right here is the instructions for this front part. Let's go ahead and fill out that first page. So at the very top, it says this of your packet.
Okay.
Yep, your packet. So let's look at the top. It defines matrix. It defines the order of them and tells you about the square kind. And then it says this one that's highlighted, it is what kind of matrix. Let's label that matrix there. What kind of matrix is that?
3 by 4.
Okay. Yep, so that would be a 3 by 4. Okay. And the entry 2, 3. So when they give us an entry, it is written as a coordinate. Okay. Again, we're reading down and then we're reading across. So we're going to find the second row down and then the third one across. So the entry 2, 3 is which number?
5.
The number 5, all right? So for that first one, it says interchanging rows, interchange row 1 and 3. So if you swap them, I have it up here on the board. You can copy or you can do there. If we're swapping row 1 and 3, what now goes on top for row 1?
Row 1's
Right here in this spot.
Um,
We're swapping row 1 and row 3. We're swapping them.
oh, so -8, -6, -7, 1.
Perfect.
And on the bottom, 2, -2, -1, 3.
Yes. So all we did was switch places for them. So the second one says multiply the row. It says multiply by row 2 by -2. So this is not telling you a whole scalar. It's just saying multiply only row 2 by negative 2. And so then we fill in that space. So for the third one, it says 2 row 2. So we're not going to change anything for row 1 and row 3. So we can go ahead and write, just copy over row 1 and row 3 because we're not changing those. We're changing row 2. And then it says add 3 times row 1 to row 2.
So multiply row 1 by 3, right?
Yes, so multiply row 1 by 3, and then we're adding it to row 2. So to that 4, we're going to add 6. So 3 times this gives us 6. So to this 4, we're going to add 3 times this number.
Okay, so we had 6 plus 4.
6 plus 4, and that's our
That's
new
10.
value.
And then 2
Okay.
plus negative 6.
Yeah, so this number plus 2 times 3.
Okay.
Yep. So 5 plus negative 1, or negative 3. There you go. Right, so you should get 10, negative 4, 2, and 17.
17. Wait, I thought the 9 was. Oh no, it's not negative.
Yeah. Okay, does that make sense on that? Okay, let me switch this. So go ahead and switch it over. Operations of 2 matrices. We're going to work through that. Okay. For a matrix to be equal, equality. Okay? Equal means they have to be the same. That means that every single number in every single space has to be exactly the same. So think about that, because if these really are equations, x plus y equals 4 has to be the same, like, or if we had this, x plus 0, if that wasn't 1 and 0, is not the same as 0x plus 1y equals 4. These are not the same. Okay? So all of our numbers have to be in the exact same spot. So if we look at this one, we've got 1, 0, 0, 1. They're all in the exact same spot. These are equal. These, we have all the same values, 1, 2, 3, and 4. We've got 1, 2, 3, and 4 are not in the same spot. 4 and 3 are not in the same spot. So these are not equal matrices, okay? This one at the bottom, all of the same values except, what is this matrix? This is a 3 by 2, and this one is a
2 by 3.
2 by 3. They're not even the same dimensions. Same numbers, and our numbers are mostly in the same spaces, but they're not the same dimension, okay? So a couple things. If they're going to be equal, they have to, every single part of it has to be equal, okay? Addition and subtraction. To add and subtract, okay? Remember, so again, if these are equations for it, if we're adding and subtracting, we have to add and subtract all the same like terms, right? I'm only adding the x's, I can only combine x's, I can only combine y's, I can only combine z's. I have to add the same like terms. So think of the space, the entries, as being those terms. Like this is our x column and our y column. We can only add the same ones. So to add, they must be the exact same size. So the first thing that we're going to check is our dimensions. Our dimensions must be identical. Then all we do is add our corresponding entries. So our row 1, and I will end up labeling them. You'll see it, me label it like this. Row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So when you see, if you see me have notes like this, that's what I mean. I'm labeling my different spots for it. That will help when we multiply. So we're going to do the very first one. So 1 plus 1 gives us 2. And it has to go in that very first spot. Okay. 0 plus 2 equals
2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2. 2
row 2, column 1, row 2, column 1, goes in row 2, column 1, everything has to match. 0 plus 3 equals 3 in that spot. And 1 plus 4 gives us 5. So when we've added them together, we're just doing the same entry. So on your paper for number 4, go ahead and add those matrices together. Right? Got the first one? Perfect. Okay. So we got 7, 0, 3, 1.
Yep.
Perfect. Okay. So do number 5. Number 5 is subtraction. It's exactly the same. Now remember, if you are subtracting a negative number, it follows all your same algebra rules. Okay. But each part is subtraction. So if we're subtracting a negative, it's going to change into a positive. Right? What'd you get, Jonathan?
-3, 8, 7, 13.
Okay. Is the 7, yep, so because we have it minus and negative, so it's positive. Perfect. Right, so scalar multiplication, we talked a little bit about that. If I'm distributing it to every single part of it, it has to go to all of them, right? So in this case, when I have a number in front and I am distributing, it's going to all of the numbers equally. So 2 in front now makes this guy
3 plus 2.
2,
2, sorry.
4,
6, 8,
4, and 2. Okay? So do number 6. It's asking you to multiply all of those times 3. All right. So now let's pull out your other practice sheet that I gave you. It has 2 problems on it. Okay. So the first one is just addition. The second one, we're combining the 2 things that we've learned. So let's label our matrices first. Our first ones are what? 3 by 1 and a 3 by 1. Can we add them together?
Yes.
Yes, they're identical. And that means our answer should also be a 3 by 1. Sometimes I find it helpful to just write out my blank ones, like I've talked to you about writing out your blank coordinates, and then we just plug them in. I know I have to have a 3 by 1. Okay, and we got 4, -4, 10.
Yep.
All right. Now, number 2 has 2 steps. Now, is this scalar to both of them? Are we going to multiply first or are we going to add first?
Multiply.
Multiply. So we use PEMDAS, our order of operations. Okay. Now, if these whole things were in a big parentheses, then we would,
Multiply both.
yeah, or we would add, or you could distribute.
Or, yeah.
You know, either way. But in this case, we're going to first multiply and then we're going to add them. So what is our dimensions for our first one?
3 by 2.
3 by 2.
Yep, 3 by 2 and a 3
3
by 2, which means my answer must be
3 by 2.
a 3 by 2. Okay. check your answer with what I have on the board. I like to do lots of color coding with these so that we can visually see where everything is going.
Yeah.
Helps a little bit. We good?
Yep.
Perfect. Well done. All right. So you can now solve any, or I would say 95% of any problem that's on the ACT with a matrix. Done. You learned everything that it was. Okay. I'll shoot you guys a couple of the
Matrix.
options this week. Actually, I can pull some up. I do have my iPad for it. So there we go. You just learned a ton. Got it? All right. So some properties of matrix operations, other things that we need to know. Associative property of addition. So can we associate them differently just like with regular addition? Yes, absolutely. So if I have 3 matrices in a row, I can add the first 2 and then the second one, or the one at the end, or I can add the other ones. Doesn't matter what order they go in, they're associating. They can also change places. So we have commutative property because all we're doing is adding those like terms, right? So I could switch them around in the equation. I'm still going to add like terms. So that makes sense. For addition and subtraction, I can move my matrices around, okay? When it comes to multiplication and division, okay, so, we have some different rules. So first we're going to look at distributive property. Again, if we have 2 matrices, we just went over that. If we have it in a big thing, we could either add them both together and then use our scalar, or we could distribute that scalar to both of them. Same thing if we have it with subtraction, right? Basic rules, these make sense, okay? Couple of things now when we hit matrix multiplications. When we are dealing with multiplying matrices, we have to know the dimensions. It's the most important things because that tells us if we can even move forward or not. Okay, so this is why we've learned to write the dimensions. So our matrices must match on the inside dimensions, and we read it left to right. This is why matrix multiplication matters. What comes first and what comes second matters because if they're switched, it might not function, okay? So when we do it, the very first thing that we do is we're going to write our dimensions underneath. So we've got 1, 0 here, we've got a 2 by 1, and we have a 1 by 2. When they are lined up side by side, these inside numbers must be identical, okay? To even tell you, that tells you, I've got a check mark, can I even do this? Can I even move forward to the next step, okay? If they don't match, like this one, we have a 2 by 2 and a 1 by 2, 2 and 1. These do not match. It is not defined. We can't even move forward. Does that make sense?
Yes.
Okay. Once we get a check mark, yes, they match. The answer, the size of the matrix of our answer will be equal to the matrix that is formed by the outside dimensions. So my answer matrix will be a 2 by 2. So did I start with a 2 by 2 here? No. Are any of them a 2 by 2? No, it's not. But my answer is going to be a 2 by 2. So what this helps us do is, I know my answer is a 2 by 2. I'm going to go ahead and write myself a blank matrix so that way I can start putting everything in the right place. Okay? So we need to know, can we even do the multiplication? And then once we do it, go for it. So let's even just look at these 2's. What if I swapped these guys? If I did this one first, I have a 1 by 2, and this one is a 2 by 1. So if we have 1, 2 times 1, 0 this way, let me move it over here. I've got a 1 by 2 and a 2 by 1. Can I multiply them?
Yeah.
Yes.
Yes. What is my answer now?
1 by 1.
A 1 by 1. It's simply 1. So when I multiply my 1 by 2 first, I get a single answer. When I multiplied this one, I got a
So
2 by 2. So we've got two different answers. So they were still able to be multiplied, but it gave us two different answers. So visually, can we see how that looks a little bit
yeah.
different? Okay. Now, I explain with number 4 how to do it. We're actually going to walk through how to do it. All right? So let's look at this one, and let's just decide, can they be multiplied, and what would my answer look like?
Can be, and it would be 2 by 4.
So yes, and a 2 by 4. Okay, Jonathan, what about this one?
No.
No. Okay.
Yes.
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 3 by 1.
And it's going to be a 3 by 1.
Yes.
Yes.
That'd be a 1 by 1.
1 by 1. Okay. Excellent. Now, here's my little labeling. Bear with me. Okay. When we are multiplying. Okay. This is why it's important. So first we do, this is a 2 by 2. This is a 2 by 1. Can they be multiplied?
Yes.
Yes. What is my answer? My answer is going to be a 2 by 1. So automatically, I'm putting my answer over here, and I know it's a 2 by 1, so I have 2 rows, 1 column. I've put my little labels in it, okay? So I would call this one, this is row 1, column 1, and this is row 2, column 1, okay? So that's why I've labeled them for it. So, if I come back to my original ones, this is row 1, this is row 2. You agree with me?
Yeah.
And for this guy, I've got column 1. Okay? So for me to get to row 1, column 1, I need everything in row 1 multiplied by everything in column 1. This is why I label it. So then that way I can get the right things together. So the number that's going to go right here, this is going to be a number, is going to come from row 1, column 1. All right? Do we see where it's coming from in the first place? Well, you're saying, Miss Thomas, we have 4 values. How do I end up with one number out of those values? Okay? We have multiplication and addition together. So the steps are, we're starting whatever is in the first space, and you kind of have to, you can use your hands, you can figure it out. The first one and the first one get multiplied.
Okay.
Everything that is in the same location gets multiplied. And then we're going to add them all up. Okay? So A is going to be multiplied times D. So this is going to be A times D. Okay? B gets multiplied times E. And then we add our 2 values together. And then that whole thing ends up being just one number.
And then we just do it
Okay.
second for row 2.
So now, so that goes in the first spot. So now, how do I get row 2, column 1? Well, I need row 2
All of column 1.
and column 1. So now the same thing. We start left to right, top to bottom.
So C.
First one is my first one,
Yes.
right? So C gets multiplied times
D.
D. And then D gets multiplied times
E.
E. And those get added together and end up to be a different number.
Okay.
Does that make sense? Okay, let's look at the next slide. I think I work it out a little bit more. Okay. So, we're gonna do it with real numbers. Okay? So, we have to label our matrices first to even decide, can we move forward? So our first matrix is a
3 by
3 by 2,
2. 2 by
2 by 2. We're looking at the inside. Yes, we got a check mark. So our answer is a
2. 3 by 2.
3 by 2. So right away, I have a 3 by 2 is going to be my answer. Okay, do we agree that this is a 3 by 2? Okay, so there's my blank spots. And I have them down here. So this guy is going to be row 1, column 1, row 1, column 2, because these are our rows. Row 1, row 2, row 3. You can even label like this. And this is column 1 and column 2. Okay? So if you label them on the outside, that also helps, you know, what matches up here. Row 1, column 1. To get here, I'd have row 2, column 2.
Yeah.
Is that a little bit?
Yeah,
Well,
that
that's a
makes
little
sense.
different visual for that. That's how I got those. Okay?
Okay.
So this is what we're looking for in these spaces. So let's tackle row 1, column 1. So I need row 1 and column 1. That's what I'm dealing with.
So -2 times -1.
Yeah? So these two.
Yes, would be the first.
So I've got 2 plus
And then it's 3 times -2, so -6.
3 plus -6. And I'm just going to leave them as the separate numbers right now. You guys okay with that?
Yep.
Okay? So row 1, column 2, I'm going to leave row 1, and I'm going to find column 2 now, because this is column 1, this is column 2, this is row 1, row 2, row 3, right?
Yep.
So what do we have for our first number here?
-2 times.
Yep, -6. It's -2 and 3. What do we have for our second number?
12.
12.
Yes, and it's always addition. Okay, and 12.
Will it
Okay.
ever be negative? Or is it just
Well, no, 3 times 4 is positive.
since you multiply it and then you have to add it to get the columns, will it ever be subtracting it to get the columns?
Mm-mm.
Nope. So
Nope.
always positive.
It's always positive, it's just if your number
Okay.
is negative. Okay?
Got it.
Jonathan, come up and do these two. Just so you'll do the next.
Okay.
Okay, so we'll have row 2, so this one, and then column
So circle what you're doing. Yep.
We get in the way of
Oh. Is that a row?
that.
There you go. Okay.
So you have 1 times -1,
Uh-huh.
which would be just -1.
Perfect.
Plus -4 times -2. So,
Excellent.
and then you have column 2.
Okay.
So you have 1 times 3, which is 3,
Mm-hmm.
and then plus, or net
Yeah.
minus 16.
You can do it that way. Okay, well done. Okay, Josiah can get the next ones. Okay, circle what you're attacking first. Okay. Yeah.
6 times -1 is -6, and then 0 times -2 is 0.
Zeros are great.
Yeah. Make it
There
easy.
you go. There you go. You got it. Okay.
Then 6 times 3 is 12. No, 6, 12.
Excellent.
Plus 0.
Well done. Okay. So now, excellent. Excellent. Okay. So now we're just going to simplify it. Right? So we have 2 minus 6 gives us
-4.
-6 plus 12.
6. Yep.
Okay. 8 minus 1.
7.
3 minus 16.
-13.
Uh-huh. The zeros
Negative
are
Negative.
fabulous, right?
Yeah, lucky.
-6 and 18. Okay? So now we have our answer. So we have multiplied these matrices, and this is our new answer. Okay? Does that make sense? Any questions on that one? And
I
then
don't remember this in Algebra 1. I don't think we ever did this.
I don't think we have.
No, you don't do this in Algebra 1.
Which is weird because it's surprisingly easy.
Don't
It
jinx
is. It is. Because
It's just like straightforward. Like there's set rules.
it is. which is why some students really go, I love this chapter.
Yeah.
It like totally makes sense.
Yeah.
Purpose, why else could we use a matrix? And we'll hit on a little bit next week too. But matrices are, companies use them all the time. So if you go into any sort of business, it's a great way to organize data with things that are different categories. So you might have a matrix where it's set up where one row is t-shirt sizes, like small, medium, large, extra large. Another row is then different columns are different colors that they offer, green, blue, white, black. And then the numbers that are in those entries are the different quantities that they might have in stock. So if you have small, medium, large, extra large, and I have it in green, blue, white, black, yellow, gray, whatever, and I have 10 small green ones. And so we get these matrices, they're the way that we can organize data that has lots of different parts of different things, and it gives us a concise view of what that data looks like. So companies use them often, or they use software data that uses it. We just haven't seen it in those terms, okay? So let's look at this guy. We're gonna practice with this one. The first guy, his dimensions is a 1 by 3 by a 3 by 1. Can we multiply them?
Yes.
Yes. Our answer is now just a single number. It's a 1 by 1. We're like, how do we get that single number? Okay. Remember that we need row 1, column 1, right? To be that single number. So here's our row multiplied by our column. Well, we're only doing it once. So that makes sense that we're getting a single number.
Mm-hmm.
Now, I've color-coded them, so we have the yellows, the blues, and the greens. That way we can see which guys multiply together. So I've got negative 1/6 times 12.
-2.
Gives us our -2. We have a 0. We love zeros. We got a 0 there. Okay. And -1/3 then goes to the -12.
4.
We have a +4. Yep. And then we add them all together and we simply get 2. So we were able to simplify all that information down just to a single number, as long as we, keep our right ones together and know which ones that we're gonna multiply together. Okay. So let's look at turn your paper over, your packet paper over for your matrix multiplication. Okay, and let's do number 1 on there. Okay, right there. So the first thing that you need to do is write your dimensions underneath. Okay, can it be multiplied?
Yes.
Okay, what will your answer be?
2 by 2.
Okay, so write your empty 2 by 2, which means you're going to have 4 spaces. Okay, and then we're going to start plugging away into those spaces. So in the first space, we are tackling row 1, column 1. If you need to label your matrices and you label this one row 1, row 2, column 1, column 2, you can do that. Yep, row 1, yep. So for the first space, we have row 1, column 1, goes in that very first space. So what are our values?
3 times 1.
Okay.
Well, wouldn't it be, since it's the whole row, so 3 and then -2, 5.
Yep, so the
times
first thing,
those.
yep, so we are gonna have 3, we're gonna have 3 numbers.
Okay.
So in this row 1, column 1, if I put it underneath here nicely. I'm gonna have 3 numbers added together, right?
Okay.
1, 2, and 3, right? To end up to be one solid number in there. So the first ones we would have 3 times 1
Which
is 3,
Yeah.
and -2 and -4.
Which is 8.
Yep, there's plenty of paper in there.
I know, I left it pretty small.
Yeah. And then 5 and 2 is 10. So we're going to add all three of those numbers.
21.
Okay. So then,
Row 2.
and it doesn't matter which order you go in. I don't care what order you go in. Just whatever makes sense for your brain. Whether that means you need to, take a little pencil and cover up, that you need to put your fingers on them to identify, whether you need to circle them lightly and then erase so you know which guys you're working with. Whatever works. Quick, you can see if I got all mine, check my work.
Matches up with mine.
Okay. What you got?
Yes.
For the most part.
For the most part.
The
Okay.
one, so it would be row 1, column 2.
Okay.
I put that into my calculator and it gave me 21. I think my calculator gave that one.
Oh, okay. 9 minus
So-
8 is 1.
And then plus 25.
Yeah, do you have 9, negative 8, and 25
That's where I missed
as
it.
your
I
numbers?
put 20 instead of 25.
Okay. Yeah, so for me, I will say the hardest ones for me are the bottom row, is dealing with this bottom row, because depending upon how they're lined up, like visually seeing how they match gets a little difficult. So I'm often just using my fingers to try to match them, because the first row, like I see it at the top, I can see where they go. The bottom rows, especially when we get down to 3s, or you're dealing with the ones in the middle, I'm like, ooh, where it's at. So
Yeah.
again, use whatever method works best for you. If that is using your transparency that I gave you guys, and using a dry erase and putting a black line on it, and having 2 of those, and so that you're actually like moving them underneath so you can see these are the guys I'm working with right now, or lightly circling with your pencil, and then you can erase and do the next section. Whatever works for you, do that, just so that we can keep them in order. Okay, does that make sense?
Yep.
Any more questions about multiplication? So on your paper packet, you've got some extra practice problems on there. And at the very bottom, so first you'll have to decide even if they can be multiplied. So if it can't be multiplied and those inner numbers don't work, just write not defined. Okay? So we don't do that. So at the very bottom you can see it says the identity matrix, and it shows you 2 of them. The identity matrix for a 2x2 is just 2 ones, and for a 3x3 is 3 ones. It's just down the diagonal. So that's all that means for that, okay? So, determinant. What is the determinant? Okay, it is a specific value that is associated with these matrices. Okay? So it's a single number that they come out to, if you have to find the determinant on the ACT, it will always be of a 2x2. That is it. They do not do 3x3s. We are going to learn 3x3s. Don't worry that you would have to do that in the ACT. All right? So it is a scalar value. Scalar just means single number. Right? We don't get hung up on the vocabulary. What does it mean? It just means it's a number associated with the matrix, and it can be used to solve a system of equations with a special formula called Cramer's rule that we'll learn next week, okay? Matrices and determinants can also find the area of a triangle in a 3D plane. So, if we have a triangle that is graphed with these coordinate points, and they say, what is the area of this triangle? We can block it all out and find it, use Pythagorean theorem to find our different sides and height and all that stuff. Or we can put it in a matrix and just find the determinant, and that's it. So, this has been a number 60 on the ACT, where they've done it in this way. And if you know, it's a very difficult problem to break all apart. If you know that I just make a matrix with the coordinate points, find the determinant, it's solved in a minute or two, okay? So that's the only time I've seen that on there. But we're gonna learn how to identify the determinant and how to solve it for a 2x2 and a 3x3, all right? So the determinant is always written like this. It looks like absolute value. This does not mean absolute value, okay? It can also be written as DETA, determinant A, so a short version of it like that. And A is always your matrix. It actually means your whole set of your matrix together, okay? If it is written like this, it might say determinant in front of your matrix, right? They want you to find the determinant. And so I have this one labeled as A, B, C, D. We are going to find the determinant. We're going to multiply, and we're going to add them together. Okay. The rule is AD minus BC. So what does that look like? It looks like these guys minus those guys, right? Now, I'm going to discuss it really briefly. This is super easy to just memorize here, but as we move into the 3x3s, it's the same rule. If I have a number line, okay, and I am going from left to right on the number line, is it negative or positive?
If you're going to the right,
If I'm going from the left to the right,
it would be positive.
I'm going to positive numbers, right? If I'm going from the right to the left,
Negative.
these are going to be negative numbers, okay? This is how I remember what to do. On my matrix, we always go in diagonals. If I start from the left and I go to the right, so I'm going from A to D, down these diagonals, these numbers are positive, okay? When I go from right to left, down the diagonal, and some will say go back up, that way it just doesn't, visually, it doesn't make sense for me like that. Right to left, down the diagonal, now the number that ends up here at the bottom is going to be negative. Okay, so that's what we're dealing with. Okay, so we would do AD, he gets to be positive, then we're going to multiply B times C, and it has to be negative. Now, if B times C is a negative number, then I have a negative times a negative, and he turns positive. So it is a negative of whatever this is. It isn't like, oh, it's negative, and if it was negative 9, he just gets to say negative 9. Okay, does that make sense? This is separate.
A negative times the negative.
It's negative. It's a negative of whatever that multiplication is. So if this is 4 and this is negative 3, this is minus a negative 12.
Yep.
Okay. So
It has to be a negative of whatever that multiplication.
But it can't be AD plus. Is that? I mean, that's basically just AD plus 12, though.
Mhm.
Okay.
Yeah. So because that negative times a negative ends up being a positive.
Right.
Okay.
So even if basically it's like even if BC is not negative, the minus makes it negative.
Yes.
Yeah.
So we're gonna go through a couple of examples
Okay.
here. Okay. So let's look at this guy. For these 2 by 2s, we have an example here. We're going to go left to right down. We're gonna do all of those first, all of our diagonals down. So left to right down, I've got -3 times 8 gives me a -24. Okay, so that is one group. Okay, then I have a 5 times 2 is 10, but he was going this opposite direction, so he had to be subtraction. So we have -24 minus 10 gives us a -34. So in this case, our AD was negative also, right? Just depends on what it is. So let's look at this one. We have 13, 4, 8, and 2. So we're going to start left to right. 13 times 2 gives us 26. We've got 4 times 8 gives us 32. And he was a subtraction. Okay? So 26 minus 32 gives us a -6. Okay? So we're going like this. Down that way, and then down. Sorry, top to bottom. Go across. Right? Does that make sense? Okay, so let's look at these on your practice for your one. So for number 1 on your practice sheet here, if we just have a single value, your determinant is just a single value. So for 3, it's just 3. It's underneath right here.
Oh, okay.
Right? So for number 2, let's find the determinant. What 2 numbers get multiplied first? -3 and 8 get multiplied first, so we're going to write those down first. And then we're going to subtract, because we're going the opposite direction. 10. Perfect. And you should always come up with one single number.
So it'd be -34.
Yes. Yes, sir. Okay. And then do number 3.
-6.
So I've got 26 minus 32. Okay. Yep. Do you know how to use your fingers in the sevens?
For
9s?
multiplying 9s, yes. 9, 18, 16,
9s are my favorites. And it shows your fingers show you the answer.
Yeah. Easy to avoid.
Okay, so that one's a big number.
-113. Or is that
50 and it should be 63. Yep,
Oh, it should have been 63.
63. Okay, so does that make sense for finding the determinant? When it asks you to find the determinant?
Yes.
Okay, perfect. Now, we just get to expand what we just learned. Same thing, okay? Nothing new. All the same rules. Okay? When we have a 3 by 3, visually, it's very difficult to figure out all of our columns. So we're gonna fix that visually by taking our very first 2 columns and rewriting them on the outside of our matrix. So that way we can have all of our diagonals, because otherwise we're gonna have to jump around to different values, okay? And that gets super messy. So we have our column 1, 2, 3. So 1, 2, 3, we're just gonna rewrite 1 and 2 on the outside of it. So on your paper, I want you to go ahead and write on for number 5, go ahead and write your first 2 columns on the outside. So what would that look like down here for number 5?
to make the 2 columns?
Yeah, so you're gonna write column 1, you're gonna write it again on the outside, so 3.
So 3, 4, 2.
Yeah.
-3.
And then we're gonna write this one next to it too. So for your A, B, C, D one at the top, let's work on this one too. So this would be, on the outside you'd have A, D, then G. We're doing the variable one at the top. Jonathan also. Okay. So A gets written on the outside, and then B, E, and H gets written on the outside. Okay, does that make sense? Now, same policy applies. If we are moving from left to right down,
It's possible.
it's going to be positive. Now we just happen to have more things that are positive, but every single one of them is positive. So A times E times I is all going to be number, and it's going to be positive. Then we have B, F, and G is all going to be positive. Then C, D, and H is also all going to be positive. Okay, so we're going to have 3 positive numbers headed in one direction. Okay, so if we had that, let's go ahead and just do the positive on your number 5. So your column, your first column, let's work them down and then put it underneath. And I like to just put them right underneath where I've drawn my line down. And I don't think that doesn't match your thing. Perfect. So you should have 3 sets of 3 numbers all multiplied down it. Okay? And all of those are going to be positive. Okay? Now, what do we do then with the next part? Now, we're going to work the backwards ones. Okay? So, we subtract everything going from right to left. They're still in our diagonals. I don't care what order that you go in. I tend to work myself inside to outside because I like to have space on my paper for it. Now, where you put it on your paper is up to you. Okay? You may do 2 different things. You may say, like I did here are all of my ones that were going from left to right. I know that they are all positive. And then now I know I'm now moving right to left, so I'm going to subtract and then just give myself some big brackets and put everything on the inside of that instead of having lots of subtraction signs. So that's an option. The other option is right when you put it underneath there, you can go ahead and do minus and do little individual ones. And this guy's got to be a minus, and that guy has to be a minus. You can put it underneath there. Personal preference. We just need to remember that when we're moving the right to left, these numbers get subtracted. Perfect. There you go. All right. So we've got negative. You had -2, 4, and 1, and then 3, -2, -3, and 5, -1, -2. Yep. So then we just simplify all of that carefully, and we come up with one single number. Right? Does that make sense? Okay, so a couple of steps. This one gets broader, but we're following the same rule. Everything left to right is positive. Everything right to left is negative. Okay, so this is an example of whenever the one that I have up here. I have everything left to right, everything right to left. I went ahead and did minus and just grouped them all together because it was easier to add them all up and then kind of get together. So we got -13 minus 12 gave me -25 for this matrix that we have as an example. Okay, so on the one that you have on your paper, which should match this one. I think you've already worked yours out.
Yeah.
Is that what you got?
Well, whenever you do like you multiply all three, and then I just add them together in my head.
Perfect.
And write down that number.
Yeah.
So I just have to do less simplifying.
Either way.
But yeah.
Again, I like to show all the steps of how it works out because sometimes when you go back home
It can
and
be
you look
confusing.
at it and you're like, now what were those numbers
Yeah.
that were multiplied together? We want to make sure that we have tackled all of the numbers. We know where did negative 3 come from?
Right.
Okay, it came from these guys multiplied. Where did negative 8? It came from those guys
Yeah.
multiplied. So we had negative 3, negative 8, and negative 60, all going from left to right. We had negative 8, 18, and 10, all going from right to left. So these are positive, even though it means it just doesn't change. So we had negative 71. Inside here, it turned into 20, but we have to subtract that. So we have negative 71 minus 20 gives us a negative 91. So that is our determinant value for that matrix, okay? Identity matrix, we've chatted twice about this. It's just everything down the row, okay? If you are multiplying two matrices, like we have learned, we have two matrices, we multiply them together, and you get your answer, and your answer ends up being this. Your answer is the identity. After you've done your multiplication, that means that these two matrices must be what? What is our rule? What always gives us the identity?
I mean, the inverse.
The inverse. 4 and 1/4, negative 4 plus 4, right? Our inverse always gives us the identity. So if on the back end you do a multiplication and you end up with one of these guys, you end up with an identity, that means those two that you had have to be inverses of each other. Right? So just one of those rules. The inverse has a written form that we should be, if we're not familiar with it, we'll start seeing it a lot more. It's written with a -1 at the top. What's great about that is every time you see a -1, it means the inverse. So a function, f of -1x, it's the inverse function. Here, if I have an exponent with a -1, it means I drop it on the bottom. I change sides for it. Okay, so our -1, all through math, if you get on a test or you get in something and it's got a -1, you're like, oh, I don't know what to do. -1 always means the inverse, all the time. Okay, it just means the inverse. I need to swap that, whatever it looks like in that form, okay? So, the great thing about an inverse is that it always undoes whatever the first matrix is, and it is the only thing that is commutative with multiplication, where the original times the inverse equals 1, and the inverse times the 1 equals 1. Okay? So when it's commutative and it works both ways and turns into 1, then that means it is a full inverse. Okay? So we can find the inverse of a matrix, and we're going to work with the inverse of a 2x2 with this very special formula. So if I start with my regular one that we know, okay, my inverse matrix, I have to first find the determinant of my original matrix. Okay? So I'm going to put my determinant in a fraction. This is all this means. This just means 1 over the determinant. So whatever number I got for that determinant, I'm going to put it as a fraction at the beginning. And then the values inside, A and D swap places.
So it would be D and A.
So it swaps to D and A, and B and C turn negative.
Oh.
Okay, so it's just a rule you have to memorize. I'm going to swap places and make those negative. So the ones that are going positive switch places,
And
the ones that were going negative
are now negative.
are now negative.
And that's only for inverse, right?
This is how you find the inverse. So let's find the inverse of this guy. So here's my original matrix. I'm looking for the inverse matrix. It's going to still be a 2 by 2 because I started with a 2 by 2. So first, I have to find the determinant. How do we find the determinant of this guy?
3 multiplied by 2.
Okay.
So that would get 6. And then 1 times 4, so negative 4.
Okay. So my determinant for this guy is
2.
2. So to find the inverse, I'm going to do 1 over 2. Right? So there's step 1 of it. Now, I'm going to switch these two guys. So 2 comes to the top and 3 goes to the bottom. And I leave 1 and 4 in the same place and they just turn negative. Okay? So now I have this. Now, when we have a scalar on the outside, we don't want to leave him on the outside. We want to go ahead and put him in. So he just means multiply everything times 1/2, right? So 2 times 1/2 gives me 1. Negative 1 times 1/2 gives me negative 1/2. Negative 4 times 1/2 is negative 2. And then I've got 3/2. So this matrix is the inverse of A, which means if I multiply these two matrices together, I'm going to end up with 1, 0, 0, 1. Okay? And so then you can work it out and try it and see if it does end up like that. Because that's the rule. It has to end up as our inverse, okay? So that's everything about matrices that we have for this week. Right? Whew! Got it? Okay, so let's look at, so on the page that says solving systems, this is not homework for this week. This is homework for next week. So we're going to wait on that one. Okay? So let's look on the back of that packet where it says 6. It's going to ask, it says, are these matrices inverses of each other? What do you need to do?
Wait, so we're not doing this week?
Yes, you
just
are.
not
Just not the
the-
very last page
Yeah.
that says systems. Okay? So on that number 6, when it says, are these matrices inverses of each other? What do you need to do to be able to answer that question?
Just multiply them out and see if it equals 0, 1, 1, 0.
Correct. We're going to multiply them out and see